Good day, everybody, and once again, we are back again to look at the November 2020 paper. We've been working really hard in trying to make sure that we prepare for those exams, and I hope that you've really enjoyed the lessons that we've, dished out in the past. All right, so for those of you who haven't subscribed, please just be part of our family. Just make sure that you take on the journey of excelling in physical science with us. Okay. And for those of you who might need assistance with mathematics or physical science, you're more than welcome to get in touch with us. And our email address is info@mlungisinkosi.co.za. All right, so we'll be looking at electrostatics. Okay, that's question 7. Okay, so let's get right into it. They say two small charged spheres A and B, right? They're placed on insulated stands, okay, which is 0.2 meters apart, as it is illustrated in the diagram, right? So they say they carry charges of -4 times 10 to the power -6 coulombs, okay, and +3 times 10 to the power -6 coulombs, respectively, right? Now, first of all, before I, start answering the question, just keep in mind that, every time we look at charges, when I've got a negative charge, like this one of A, what it simply tells us is that we've got electrons that are in excess, right? So it means that there are more electrons than we have protons, for instance. And obviously for a positive charge, it means that we've got an excess of protons, or you can look at it as a deficiency of electrons, okay? Because we mostly talk about electrons, or in this case, we assume electrons to be the ones that move. In this case, we simply say that here there's an excess of electrons and there's a deficiency of electrons, okay? Right, now let's start with the first question. They say M is a point that is a distance of 0.1 meters to the right of sphere B. So there's point M there. Okay, so we want to know, they say calculate the number of electrons in excess. Do you see that? So they're telling us that electrons are in excess in A. Right, so you've got an equation right at the back. If I may just show it to you. And this is the one, right? So it simply says the number of electrons is equal to the charge divided by the unit charge of an electron. Okay, in this case, of course, it's the value 1.6 times 10 minus 19. So I'm going to use that equation. Okay, so we know in this case, I'm going to say for 7.1. So we're looking for the number of electrons. So N is going to be the charge divided by the unit charge of an electron. So our charge, this is -4 times 10 to the power -6 divided by the unit charge of each electron is -1.6 times 10 to the power -19. Remember, you're given that in your table of constants, right? And we get an answer. Okay, let's have a look at it. Okay, now answer is 2.5 times 10 to the power 13 electrons. And please, I want you to keep in mind we are looking for the number of electrons. So if they wanted to find out the number of electrons that are deficient in B, for argument's sake, of course you'd also take the charge of B, but in this case you would divide by positive 1.6. The reason for that is that you can never have the number of something. For instance, if you're counting people, right, you can never have -13 people, for instance. It wouldn't make sense, right? So in this case, you must always make it a point that your answer is actually positive, because it's talking about a finite number, right? In this case. So yeah, I hope that makes sense to you. Right, so let's go for 7.2. Okay, so they say calculate the magnitude of the electrostatic force exerted by sphere A on sphere B. Right, so in this case, we're looking for the force between the two. Of course, we're going to apply Coulomb's law, right? And what we simply say is that the force between A and B Okay, let's say electrostatic force, that's QA, that's charge of B divided by R squared, the distance between them. So we know the Coulomb's constant is 9 times 10 to the power 9. Now, in this case, as I did say, if you haven't watched our videos on electrostatics, please just have a look at them. We did say we just substitute the absolute value of each charge, meaning that you disregard the sign. Okay, so what the sign helps us with is to determine, the type of force, whether it's attraction or, repulsion. So this is going to be 4 times 10 minus 6 multiplied by 3 times 10 to the power minus 6. Okay, and the distance, remember they said between A and B, so the distance between them is 0.2 squared. Okay, and let's try to work it out quickly. I get a force of 2.7 newtons. Now, I want you to please note, in this case, they said the force that A exerts on B, right? Remember, according to Newton's 3, the force that A exerts on B will be equal to the force that B exerts on A, right? Obviously in opposite directions, but please keep in mind that those forces are exactly equal. Okay, so it doesn't matter if they said the force between A and B, or the force that A exerts on B or B exerts on A, you should be able to get exactly the same. And because they said magnitude in this case, I'm not going to worry much about the direction. Okay, right, now let's go to the third question. They say describe the term electric field, right? Please remember that electric field, okay, we say that it's the area where electrostatic force is felt per unit charge, okay? Or you can say where force is felt, electrostatic force is felt per unit or by a test charge, right? Okay, a positive test charge, that is. All right, now we say calculate the magnitude of the net electric field at point M. So we're looking at point M, and remember, in order for us now, I'm gonna start calculating it there. Okay, so for 7.3, so first of all, let's consider M as our point. Of course, they did tell us that's our point. So what's the assumption at point M? It's that we've got a positive test charge there, right? So the question is, how will A affect that positive test charge? You can see that the field due to A would attract that positive charge, right? So it would pull it towards itself. So I'm going to say, well, it means that, now think about it, okay? If we're looking at A and M being positive, right? So we're saying M being a positive test charge, we're assuming M would be the one that moves, right? Okay, remember, positive test charge, it's an imaginary charge. It doesn't actually exist, right? So A would attract this guy, so this guy would be pulled towards the left. So it means that the field, okay, due to A should be a field to the left. Okay, I don't know whether you want to say to the west, okay, or to the left. Right, so that's the field due to A. Now let's look at what does B do to M, right? So if we consider a positive test charge there, okay, what are they doing to each other? They are repelling each other, but we're assuming we're looking at M, right? So what would M do? It would actually be moving away from B. Okay, so as it's moving away, in this case, it means that it will experience a field to the right, or you can say a field in the easterly direction. So in this case, this is the field due to B. Now, if you notice, in that case, it means that the net field would actually be the difference between the two. And why is that? Because they are heading in different directions, right? If they were going in the same direction, so we would add them. But alternatively, what you can do is you can just choose a direction. Say, for argument's sake, if we take direction to the right is positive, right? Okay, so we're going to say it means the net field would be EB, positive EB, plus a negative EA, right? The field due to A. All right, so now let's find out what the net field is. Let's calculate the field due to A. That's going to be K, the charge of A divided by R squared. Now that's 9 exponent 9 multiplied by the charge of A. We said that's 4. Okay, and remember, once again, you just substitute the absolute value of the charge and not the sign. What the sign is for is that it helped us to determine the direction of the field. Okay, so the distance between M and A, I want you to note, so that's that 0.2 plus the 0.1. So this should be 0.1, 0.3 rather, squared, right? Let's find that answer. Okay, and my answer is 400,000, or you can say 4 times 10 to the power 5. So that's 400,000. And remember, field is measured in newtons per coulomb, right? And I'm going to state direction there. Okay, and remember, our direction is to, we said to the left, okay? Or you can say to the east, to the west rather. All right, now, obviously now we're going to also find the field due to B. Okay, let's substitute that. So that's K cube B over R squared as well. Okay, so they're saying 9 times 10 to the power of 9. Okay, and the charge of B is 3. Okay, I'm just gonna bring that closer again so that you can see the picture. So that's 3 times 10 to the power negative 6. Okay, divided by, now the distance between B and M, that's 0.1. Okay, so this is 0.1 squared. Okay, right, let's find that field again. And I get a huge number. Okay, and this number actually makes sense because the distance is shorter. I get an answer of 2.7 million. So so that's 2,700,000 newtons per coulomb. Okay, or you can say 2.7 times 10 to the power 6. Okay, that's newtons per coulomb, and in this case it must be to the right. Okay, right, I'm trying to scramble for space here. Right, if you don't mind, I'm just going to continue over the other side. Okay, so what we now wanted to find was remember the question was to find the net field, right? So now I'm going to say, all right, we've got the two fields. So to get the net, okay, we're simply going to say, all right, so for our net field, we're going to take, we said taking right as positive, so that's going to be EB, the positive direction, plus a negative EA, if you want to look at it like that. Or we can just simply say, because they're in different directions, we're going to subtract them. So we're going to say 2.7 times 10 to the power 6. Please don't mind, I'm just converting this into scientific form. Minus, in that case, we had 4 times 10 to the power 5. Okay, and our final answer, okay, will be 2.3 times 10 to the power 6 newtons per coulomb, and it obviously will be in the direction of the bigger field. We get our answer as positive there, so it must be to the right, or you can say to the west. Okay, to the east rather, in that direction. Okay, right, so I hope that kind of makes sense to you. Right, so let's continue. I'm just gonna move it over to this side. Okay, The last questions, they say now the charged spheres A and B and another charged sphere D, okay, are now arranged along a rectangular system of axes as shown in the diagram below. So there's A and B there. And you remember that A and B, obviously because they were oppositely charged, in this case the other one negative and the other positive, they exerted forces of attraction to each other. Okay, so A would experience a force in that direction, okay, in that direction due to B. It makes sense. But now they say that the net electrostatic force experienced by A is 7.69 in the direction as shown above. So now you have a resultant force that is in that direction. Okay, right. Before I just look at the the question, what this would mean is that if you look at sphere A, it would be actually experiencing two forces. So this would be the force due to A and B. Okay, let's call that force AB, or the force that B exerts on A, whatever you want to call it, right? But in order for the net force to be in that direction, it would simply mean that the other force would have to be actually a force upwards, right? Such that if you were to complete a parallelogram, and again, if you don't understand this section, please go and look at our video on electrostatics, okay, where I explain how to calculate net force and net field. All right, it's in a playlist. You can go and check out the electrostatics playlist and you'll find it there. Right, so in this case, our net force would be in that direction, which is the one that we're given there, 7.69. So it means that the other force, or the force that D exerts on A, let's call it FDA, all right, in this case would be a force that is vertically upwards. Okay, now they're asking us a question here and we needed to find out, okay, is the charge on sphere D positive or negative? Now think about it. A is already negative, so in order for it to experience a force upwards, it means whatever it is D is, what D is doing is that it's pulling A towards itself, right? So it would mean that this would be a force of attraction. So as a result, if this is negative, it means that D should be positive. Okay, I hope I've explained that well enough. Okay, so it means that that's a positive charge. Okay, now they say to you, calculate the magnitude of the charge on sphere D. So we already know the force that exerts on B, that A exerts on B, right? Remember we calculated it earlier on. Where's that force there? Right, it was that 2.7 Newton force there, right? So we know that this force is 2.7 newtons, okay? And we know that the resultant force, okay, remember that resultant force there is given as 7.69, so we know that the resultant is 7.69 newtons. Okay, so now we want to find out, let's find out what would be the magnitude of this force. And remember, to get that resultant, what do we normally do? To get that resultant, if you think about it, this is sort of a 90-degree triangle. Whether you look at this triangle here or this one here, because what a parallelogram does is that it breaks those two triangles into, two equal triangles, right? So in this case, this side is equal to, of course, FDA. So this would be a 90-degree triangle, isn't it? So it means to get the F net, in that case, you'd say F net squared. It would be the force that B exerts on A squared plus the force that D exerts on A squared. But I already know this force. It's 7.69, the magnitude of it. Okay, that's 7.69 squared. I know the force that B exerts on A, that's 2.7 squared, right? So we can find the force that D exerts on A, right? So I can subtract that and take the square root, okay? Right, so you're going to say 7.69 squared and subtract 2.7 squared, okay? And I'm just going to take the square root so that we just end up with the answer. Okay, so I get the force that D exerts on A. This force is equal to 7.2 newtons. Okay, now remember I'm looking for the charge, right? So I've got the force now. I'm looking for the charge. So I'm going to say, well, the force that D exerts on A, let's apply Coulomb's law. That's QD QA over the distance, right? R squared. So now I've got the force, that's 7.2, okay? And I've got, of course, this is 9 times 10 to the power 9 multiplied by, I'm looking for the charge on D. In fact, let's calculate that. Let's use the charge on A. Remember, the charge on A was 4 times 10 to the minus 6, okay? And then the charge of D, that's what we're looking for. And all right, divided by, now remember the distance between them. Let me get this one closer again. So the distance between them was given as 0.15 meters. Okay, so obviously divided by that 0.15 meters squared. Okay, and all we need to do now is some mathematical gymnastics. Okay, let's have a look at it. Okay, if you cross multiply that, you multiply with that, and you'll divide by that whole thing. I'm sure you know what to do here. Okay, so let's just work out the final answer. And my final answer on the charge on D is 4.5 times 10 to the minus 6 coulombs. Okay, that is the answer. And remember, it's actually positively charged. All right. Obviously, if we had found out that A was, or rather D was negative, then you'd need to put the polarity there. But I mean, the question wanted just the magnitude, so it's not an issue whether it was positive or negative. Okay, right. So I hope you were able to follow on and enjoy that. Okay, and for those of you who haven't subscribed, please do the right thing. Okay, and I'll see you guys next time. Sharp, sharp.